After completing this lesson, you will be able to start a simulation in Autodesk CFD, analyze your design to identify the most aerodynamic outcome, and review the results of the analysis. We'll continue with the model in CFD that was set up in the previous part of the lesson. If you didn't complete the setup portion, please do so now. We'll begin by selecting Solve from the Simulation panel in the toolbar. After clicking Solve, a Cloud Job Cost dialog will appear. Depending on the type of simulation you're running and the type of computer you're working with, you may choose to run the simulation on the cloud. The cloud will allow you to run the simulation against your Cloud Credit account without taxing your system to do this. We'll select OK, and the dialog will appear. We'll change the solution mode to transient. Since this is going to be a very short endurance analysis, we'll set the time step size to 0.01 seconds. For this analysis, I want to put in a specific time span. We'll put in 1.2 seconds. The analysis will run until it runs out of time or until it runs out of time steps. Then set inner iterations to 2 and expand save intervals. By establishing save intervals, we can go back through the time of the analysis and pick certain steps to review the results at that point in time. With this type of transient analysis, this can be very informative to see how the results change over the course of time. We'll make sure the save intervals are based on seconds, and then put the results value to 0.08 seconds. To make sure that this analysis runs all the way through the time steps, we'll add some additional time steps, setting the value to 130, and then clicking Solve. When you click Solve, the output bar will re-expand, showing that the mesh is being processed and the model is being set up. Then the output bar will automatically switch over to show the convergence plot. As the time steps are being processed, you can see all of the various values changing and updating as time goes on, and you can also see in the image above how the velocity of the air is changing and how it flows over the body will change over time as well. This analysis in real time took 12 minutes to run. When it's complete, we can close the output bar. We're now in the Results tab of the interface, and presently we're looking at a global result, and looking at the panel on the end of the toolbar, we can see that the results display is based on the velocity magnitude. We can change it to other values, isolating the velocity through planes, isolating the individual values of the velocity. But I'll switch it back to velocity magnitude, and then switch the results to planes. Clicking the Add icon will display a plane in the middle of the volume. Using the arrows, we can move this plane through the space. We can also go up to the Iteration Step panel in the toolbar and switch between various time iterations. As we click through, we can see how the velocity begins to accelerate as it moves over the tires and the side pod of the model where the plane is currently located. The plane can be relocated, it can even be turned, and you can add additional planes to the model as well. As you add planes or any of these results displays, they're added in the Design Study bar in the lower left, where we can click them on or off. We can also change how the volume is displayed. Changing it to transparent allows us to see where the volume is, and it offers us other opportunities to overlap displays. So we'll leave the global display on transparent, and then click on Traces. We'll switch to a diamond pattern, and set the seed density. The seed density value is a unit based on the space between the seeds, so the higher the number, the fewer seeds that are displayed on the screen. We'll set the value to 2 and click on the front face, dragging out a rectangle. With the second click, you can see the traces that are laid over the bodywork. We can right-click and change the volume to Outline to more clearly see how the traces are moving over the body. We can also display ISO surfaces or ISO volumes. And finally, to help us calculate a coefficient of drag, we'll go to the wall calculation. First, we'll select the double check mark to add all of the surfaces in the model to the calculation. Then, selecting the single X icon, we'll remove the faces that make up the front, top, bottom, back, and outside of the fluid volume. When this is done, we'll tell the Wall Results tool that we want to calculate out the force. Select the units, we'll use Newton, and then click Calculate. This will give us a calculation of the area and force applied to each individual surface, and it will give us a summary of the model. You can also save these values out as a file for reference in your calculation. An important note is that if you return back to Fusion 360 and update your design model, your simulation model will update as well. That change can then be used to update the CFD study without having to update any of the boundary conditions. This will allow you to quickly iterate your design and quickly test out the aerodynamic properties of your car as you develop the design.